Okay, continuing on today with our Laplace Transform playlist. We have here the Laplace Transform of cosh AT. Now for this one, I actually already did a video, but there was a bunch of different errors in it, and I actually had the wrong answer in it. So I just wanted to redo that video. I'll delete that one and add this one to the playlist. Now over to the right, we have a few formulas that I'm going to use, sort of. This first one I'm not actually going to use, but this is what we found in the previous video for the Laplace of sinh AT. We just got a over s squared minus a squared. And then for this other formula, we have the Laplace transform of EAT. We found this one in another video previously. And for that, we just have 1 over s minus a. But we have this important condition on it that we need s to be greater than a in order for this to converge. Because with the definition of a Laplace transform, you're integrating all the way to infinity. So there's a lot of opportunities for those integrals to diverge. So it's important that we have this condition. So if you want to see how we found these two formulas, you can go back into the playlist. There's videos on each of these. And you can also check out the whole playlist. I'll provide a link in the description. And then last, down here at the bottom, because we're looking for the Laplace transform of cosh AT, I just want to do this using the definition of cosh in order to write this in a different form. And so what we can do is we can use this to start, and we can plug this in and replace the Laplace. We can plug this in and replace with cosh AT. So doing this, we'll just rewrite this, and we'll have here the Laplace of EAT plus E minus AT. But for this 2, I could write this in the denominator, but actually because it's a constant, I can bring it out front of the Laplace transform. And next, because we have addition here, we can break this up into 2 Laplace transforms. Because Laplace transforms are just integrals, we have most of those same properties, so I can rewrite this as half Laplace EAT, and then I can distribute in the 1/2 and write it as 1/2 times the Laplace of E minus AT. But then for this right here, we have exactly our formula over here to the right that we can use. So this is going to become 1/2, and then we'll have this, 1 over s minus a. And let's just make a note of that condition. We've got s greater than a. And then really on this other one, we can use the exact same formula. We have minus a instead of a. So what we can do with this is use the formula, but replace a with minus a. So what's going to happen is this now is going to become 1 over s minus a. And then with the condition on it, we're going to need s to be greater than minus a. Minus times minus is plus. Then I'll factor out 1/2. I probably should have never multiplied it in, but whatever. So we'll factor out the 1/2. Then let's get a common denominator. So for 1 over s minus a, I'm going to multiply numerator and denominator by s plus a. So we'll have an s plus a here. And then doing the same kind of thing on this one, we'll have 1 over s plus a. But then I'll multiply numerator and denominator by s minus a for the common denominator like this. But now with the common denominator, I can put these two together. So we'll still have our 1/2 out front. I'm actually going to multiply out the denominator now. So this is going to become s squared minus a squared. We'll add all the numerators up. So s plus s is going to give me a 2s. A minus a, that's just going to be 0. So we'll leave that off. But then here, the 2's are going to cancel. And so we have our formula for the Laplace of cosh AT. It's just going to be s over s squared minus a squared, but we do need to look at this condition because we have s greater than a and s greater than minus a. Well, it turns out what we can do for this is we can just write this as s greater than absolute value of a. The reason this is going to work is we can look at this in cases when a is greater than 0, then we can just drop the absolute value on this and we're saying s greater than a. When a is less than, we could say less than or equal to 0, then we can drop the absolute value and put a minus on it, and then we get s greater than minus a. But this is the same as this is the same as this, so we'll use this condition on this formula. So there you have it, Laplace transform of cosh AT. Thanks everyone for watching. Have a good day.